Hello. Now, today we're going to be doing something called differentiation by first principles. And it's a kind of a derivation of everything that's going to come later in this chapter. So it's the fundamental basis that we make all of our future arguments from. So it's quite important, and it can come up as a separate exam question. Now, what we're going to do is combine the two elements that we have been discussing so far in differentiation. That is the average rate of change, which we already know of as the normal slope equation, and combine it with the concept of limits. That's all differentiation by first principles is. Take the normal slope equation and use limits to let the 2 points get as close together as we like. So at the moment we have a slope equation. If we go over to our graph here, if we have our point at x and f of x, and our second point at x plus h, and our second y point at f of x plus h, we know how to get the slope between these 2 points. We'd have x1, y1, x2, y2, and we'd sub into our normal slope equation. All we're going to do is allow these points to get arbitrarily close together. We're going to use limits to let our points get infinitely, effectively, close together, so that it's like getting the slope of a line at a single point, which we can't logically do, but we can use limits to get an infinitely good approximation of what the slope would be at a particular point instead of at 2 points, which is what we've got at the moment. So again, we're going to use the normal slope equation and limits to get the slope at a point instead of at 2 points, which is what we're used to. Now, a little bit of a word on how I've marked my points here. My first point is at x, and I'm able to read this coordinate very straightforwardly. In the door x, up the stairs f of x. Perfectly normal. We've done this for years. Now, a point x plus h is a little bit different. So what would we mean by that? If I draw in blue, I start at x and I walk along the x-axis a distance h. Well then, this point here, this x value here, is going to be x plus h. If I started at x, moved along h, I'm at x plus h, and my y value is just going to be f of x plus h. So I now have my 2 points defined. So let's just put them into the normal slope equation. Nothing different. So I have my slope here, and I have it defined in my different ways that I often do. I could also have it written as rise over run. All of these mean slope, and what we're going to find next also means slope. So let's sub in. We have our delta y over our delta x. Change in y all over change in x is going to be y2 minus y1 all over x2 minus x1. So I'm going to have y2 is f of x plus h minus y1 is f of x all over x2 is x plus h minus x is x1. So this is my slope equation written in this kind of funny function notation kind of way that's going to be useful for when I want to write it in terms of limits. Now, I can simplify this bottom line a little bit, and I often will, so I'm going to rewrite that. Delta y all over delta x is equal to f of x plus h minus f of x all over x minus x is 0, and I'm just left with h on the bottom line. Now, this is the normal slope equation. We haven't done any new maths. All we're going to do now is let these points get closer and closer together. Now, how are we going to do that? Well, the gap between them is h. The gap between our x values is h. So if I let h tend to 0, in effect, I'm going to be bringing my points closer and closer together. The gap between them is h. If the gap between them tends to 0, then the points get closer and closer together. So I'm going to let the limit as h tends to 0, sorry, not equals, limit as h tends to 0 of f of x plus h minus f of x all over h. I'm going to call that f dash of x, little comma, and I'm also going to call that dy dx. These are two names that mean exactly the same thing, and they are going to be the slope of my curve at a particular point. The way that I'm going to say it in English is they're going to be the slope of the tangent to the curve at a particular point, but we're going to come back to that in a little minute. This is just the slope equation where I let the 2 points get as close together as we like using limits. That's it, and these are the two names that we need to know for it, f dash x and dy dx. You can see that dy dx is very closely connected to delta y all over delta x, and there's a reason for that because one develops out of the other. Now, let's put this into practice. So I have f of x is equal to 2x plus 3. And I'm doing something that's going to give me the slope of this line. But this is a straight line. If I switch to GeoGebra for a second, so the screen is going to get brighter for a moment. This is the equation of my line. Sorry, this is the graph of my line. Y is equal to 2x plus 3. What is the slope of that line for any value of x? Well, it doesn't matter what points I pick. I rise 2 and run across 1. My slope is just 2. Switching back. So this is also in the form y equals mx plus c. So I know already my slope is going to end up being 2 or 2 over 1. So I know that dy dx or f dash x, whichever way I write it, is also going to end up being 2, because dy dx and f dash x are just the slope of our function. That's all they are, that's all they will ever be. They're the rate of change or the slope of our function. But let's do this algebraically. So if I want to know what the slope of the tangent to the curve is for my straight line here, I know it's going to end up being 2, but I can use this formula here to find it. So f dash x is going to be the limit as h tends to 0 of my slope function so limit as h tends to 0 of my slope function. Now this gets very messy because there's a big complicated fraction going on. So what I recommend you do is write down the different parts of this and simplify it a little bit before you sub it into your equation. So f of x is just x plus 2x plus 3. F of x plus h is equal to 2 on x plus h. Anywhere there was an x, you sub in x plus h and simplify it down a little bit, and we get 2x plus 2h plus 3. And the bottom line we know is going to simplify to h. So our next line then becomes limit as h tends to 0 of 2x plus 2h plus 3 minus f of x is 2x plus 3 all over, this simplifies down to h. I can see I have 2x minus 2x and 3 minus 3, so I'm left with 2h all over, limit of 2h all over h. I can see I have a common factor of h top and bottom, so I have my limit as h tends to 0. I divide out my common factor and I'm left with 2. There's nothing involving h here, but I can just take the limit, so let h tend to 0. There's nothing to tend to 0, so I just end up with the constant 2. So f dash x or dy dx, depending on the way we wrote it, would just be equal to 2, which we knew because we know that dy dx or f dash x is just the slope of the line, and we know the slope of our straight line in the form y equals mx plus c is just going to be 2. So this works out. This is a good test that we're not making mistakes, because we get what we would expect to with our straight line equation. Now let's try something a little bit different. We're going to have a look at our quadratic. Now, if we're getting the slope of our function 2x squared minus 4x plus 3, what complication immediately comes to mind? Well, if I flip to the GeoGebra for a moment, so the screen will get brighter, it's a quadratic curve. So the slope is going to change as x changes. The slope here is negative. The slope down here is 0. The slope here is positive. So as x changes, our slope of our curve is going to change. So we would expect then, we're going to switch back, we would expect then that when we get our slope of this function, we're going to have x involved in it. It'll depend on x because the slope changes as x changes. So let's try and find it, and then we'll try and find what the slope is at x is 2 and x is 1. So to find our f dash x, or dy dx, we're going to use our limit of our slope formula. So the limit, as h tends to 0, of our f of x plus h minus f of x all over x plus h minus x. Again, normal slope formula, just written in function notation. I'm going to write out what my f of x plus h and my f of x are. So I've written out my f of x, and I've written down my f of x plus h and simplified it down as much as I am able to. And now I'm going to sub into this equation here. I strongly recommend you multiply this out in the way that I have before you substitute in, or this fraction becomes nightmarishly complicated to keep track of. So my f of x plus h is 2h squared minus 4x minus 4h plus 3, and I subtract away my f of x, 2x squared minus 2x squared minus 4x plus 3. I simplify this down and I end up with all over h. And I look for my like terms that I'm able to subtract away from each other. I end up taking them away and them away, them away, and I am left with the limit as h tends to 0 of 4hx plus 2h squared minus 4h all over h, divide out by h, divide out my common factor of h top and bottom. So the limit h tends to 0 then of 4x plus 2h minus 4. Let h tend to 0, and this term tends to 0, and I'm left with 4x plus 0 minus 4 equals 4x minus 4, and that is my slope function. Now this time it's a slope function because it depends on x, because we know that our quadratic curve is going to depend on x. Now if we put in f dash of 2, what is the slope of our tangent to our curve at x is equal to 2? So we sub that in, it would be 4 by 2 minus 4, and it ends up being equal to 4. And f dash of x is equal to 1, we'd end up with 4 on 1 minus 4 would be equal to 0. Let's double check that on our graph. So what we have just found is the slope of our tangent line here. We've let the 2 points get infinitely close together. They're effectively at 1 point. So we have the slope of a line touching at 1 point. And we can see that the slope of that line at x is equal to 2 is 4. And then if we move our point around to x is equal to 1, we can see that our slope would be 0. The slope of this line would be 0.